Hi, welcome to Solving Science, trying to answer anomalies and the unexplained mysteries of the cosmos using expanse tension theory. Today, neutron stars, an entire class of stars which are the dense stellar remnants of the collapse of massive stars, generally bigger than our sun, between 1.1 and 2.5 solar masses. These are incredibly dense remnants, which means they're quite small. Radius of between 10 and 14 kilometers, diameter up to 28 kilometers. So tiny little things, really, but incredibly dense. The problem we're addressing, general relativity, the standard model, simply can't explain what we observe at all. Against an entire class, a whole group of neutron stars. From one end, zombie stars that aren't doing very much, dead pulsars, to highly energetic and violent magnetars, up to the boundaries of where we see the event horizon of black holes. What are the anomalies we can't explain? They include irregular spin-up glitches, rarer anti-glitches, timing noise, quasi-periodic oscillations and abrupt torque reversals, unexplained cooling rates, intermittent or bursting radio emissions, and extreme magnetar flares releasing huge amounts of energy, and transient quasi-collapse events. By the way, these huge amounts of energy, they could release the entire world's annual consumption of energy within 1 second. So huge amounts of power. Now, here is the range of neutron stars as a class. I'm not going to read all of them, but I'm going to go through a few because let's take some time. Now, these have been organized in density order, from lowest density at the top to highest density at the bottom. And if you've been watching Expanse Tension Theory, you know why I've done that, because you know what's coming. So at the top of the list, we've got zombie stars, also known as dead pulsars. They're ultra cold. They've lost nearly all of their magnetic activity. And they don't do very much at all. They're basically invisible to us, apart from very minor residual heat. We then have young neutron stars that are the embedded remnant of a supernova. Again, that remnant at the heart of a super red giant. Very soft thermal X-rays. There's hardly any radio or gamma emissions coming from them. Unusually weak magnetic fields from them. We build up slowly to rotating radio transients, very brief, infrequent radio bursts, very strange, maybe a burst every minute, every few minutes to hours, building up in energy through ordinary radio pulsars whose radio beams periodically pulse against Earth. We can go through a range of different neutron stars. Let's go to the high end where we see highly energetic, violent bursts of energy coming out of magnetars, where you've got giant X-ray and gamma ray flares, dramatic timing noise, huge magnetic fields, enormous magnetic fields, ultra energetic outbursts, and often very short lifetimes because they are so violent. Okay, now, one thing I've noticed is across that range, I can group these, and I can lazily group them into 3 groups. At the top, I have fading intermittent neutron stars that are showing signs of very low energy. There's not a lot happening. Zombie stars kind of give you a clue, and dead pulsars. In the middle, we have regular to erratic pulsar behavior. Regular moving to erratic as we increase in density through this regime. And again, the density tracks through here, and I'll mention that in a minute, up to this violent magnetic and structurally unstable set of neutron stars as we approach density. Density up here, 10 to the 14 kilograms per meter cube. Density down here, you're up at 10 to the 18. So huge orders of magnitude difference in the density across that range. And behavior going from behaved, dead, still zombie behaved, through normally behaved to erratic to violent. Now, if you've been following expanse tension theory, we posit that matter can couple or uncouple from an underlying expansion field of the entire universe, triggered expanse tension ripples at the point of the Big Bang, and we actually have what we propose is a quantum field of energy, which is driving expansion of the universe. And those expanse tension ripples have energy. They can hold energy in a way unlike space-time. Now, there are 5 coupling gates depending on the environment and the matter that from plasma and radiation era to matter era and galaxy era. But there are these switching functions where, depending on the ability of the medium of the time of that density of space, where they have a threshold where either matter strength standard model forces hold back and win, or the expansion field wins, and they are now set in a frozen core of value. So this is what we call switch E. It's a switch from low moving to high density, and the coupling kicks in where you have higher density kicking in. You have, in this stage, matter tightly coupled to expansion, this underlying expansion field. Now, what does that mean for neutron stars? Well, what you have is, through that field, oh, by the way, the neutron stars exist on that S-curve, and they exist all the way along that S-curve to the top. And you see that glitch amplitude, so the amount of glitchy, erratic behavior increases as they go along that, and we can plot that density. And what I'll mean by that, and again, what I describe is we have a continuous physical ladder of quantum mechanism that's causing glitchiness in neutron stars. So to explain, here you have dead, cold pulsar zombie stars, very little energy, moving through the ordinary pulsars. Young energetic pulsars are then happening at the transition. And as you then get violently energetic, magnetic, bursting energy, you have the magnetars up here operating in the very highly coupled region. The coupling with expansion gives them their energy. Now, what we see here is that there's also a transition across the radius of neutron stars. So the inner dense core of a neutron star can be up to 10 to the 18 kilograms per meter cubed within that star. So phenomenal amounts of density in the very core. But if you move out towards the outer crust and the outer layer, you're moving back out to 10 to the 14, 10 to the 15 amounts of density. Now, that transition, that gradient, exists along the radius, but within the neutron star. Now, the last time we saw something like that was the switch gate that operates within a galaxy, but it operates the other way around. The outer regions of galaxies experience coupling, which holds and sustains that outer region speed attributed to dark matter. Now, in this switch, it's operating the other way around. We've got high density triggering greater coupling, but the difference here is it's the high dense core which is experiencing the coupling, not the outer shell. So we have layers of shells, a tug of war, a strain, a tension happening within the neutron star, but the high energy is at the core, it's at the center. Now, what we now can track from low dense to high dense is a set of behavior which can be explained by that inner tension strain that's happening within the star. At the midpoint, the mid shells are cutting through strong differential strains, and that can cause glitches. But as we move higher and higher in density, we have massive stress reservoirs, and the crust can actually slip and trigger these flares and these glitches, huge bursts of energy that are emerging from magnetars, because we're moving down this stress and gradient boundary to ever more energy loaded systems. Catastrophic bursts of energy, because the inner core of the neutron star is, violently building up tensions from this very, very tight coupling to expansion of the universe, to these expanse tension ripples. The outer shell, mostly adhering to general relativity principles, is a passenger in this violence and turbulence happening in the shell just under the surface. Now, we can track Again, against each set of stars, we can track against the density of the region. We can now look at what the standard model of general relativity struggles with and what can't it explain against the anomalies of glitches and radio bursts and noise and cooling anomalies. And we can see these increasing with density. But what expanse tension theory does is against gate E, it has a correlation. It detects the pattern. It can see that the low density neutron stars are behaving themselves and they're operating closer to general relativity. And as you work through this, gate E, this switching gate, can explain what's happening. So we've got inside out coupling, and it's the core that couples first. The differential tension produces shear stresses. Again, the difference, the delta between coupling in the inner core and the outer core, which creates and actually resolves those temperature, cooling and erratic behavior differences. Where we see glitches or flares, it's often where you have dynamic instability as the neutron star's core condenses and collapses. You have a shift in where that transition lies, explaining structural change, breakdown and collapse driven from the inside out. That can all explain star cooling, contraction, density increases and movement of within the shell, which again can explain glitches. Now here's the other thing. Within that switching regime from zero, uncoupled mass to the expansion field, to coupled from 0 to 1, what we see, zombie stars and ordinary pulsars, we see these glitches are in a relatively low gradient regime where the difference in the coupling strength is fairly low, only about 10% of coupling difference. So very low tension gradients, again, not very much glitchy behavior. All the way through young energetic pulsars, where you're starting to see a 40% increase in coupling gradient difference from the core to the crust and the outer regions. Again, where you start to see more and more glitchy behavior. Right up to the magnetars, where you've got a 60% delta, a 60% gradient, driving tension and strain, driving highly erratic, huge bursts of magnetic radio gamma ray radiation coming out of neutron stars. So we can explain those gradients passing through more dense neutron stars, through the collapse, and explain why we see this irregular behavior. Now, it's nice to get to this chart. What we see here is an ordinary pulsar transitioning in density through its radius, coming back to the core. You see the core only 50% coupled, so halfway through the coupling gate where mass and matter, mass and expansion are coupled, again giving it some glitchy behavior. But if you work your way through these higher energy pulsars up to the outer region of these magnetars, you see immediate, very tight coupling to the expansion field. And again, it explains why they're so violently energetic and unstable. So where have we got to? We think across a range of 14 or 15 different classes and types of neutron star. By the way, this includes dark stars, which again at the extreme violent end beyond magnetars, so dark stars. Let's not bring in dark matter and dark energy again into this. Again, at these hypothesized extreme magnetar nearing collapse, they're on the verge of kind of event horizon black hole territory. Very short lifestyles, life cycles, can be explained as part of an overall continuous coupling function of matter to expansion of the universe. Now, I don't think there's a single framework in the world today that can explain the whole class of neutron stars from zombie star up to dark stars in a single continuous framework. Now, that's one very powerful thing to say. I think expanse tension theory has the potential theoretically to explain neutron stars. I think it can explain their behavior down to a quantum field level. This isn't maths, this isn't geometry per se. This is a quantum field theory based mechanism. It's linked to the density of matter, coupling or uncoupling to a quantum field, and the maths work. They explain what we're seeing. We can explain the observation with a single framework. But let's also remember that same framework can explain outer rotation of galaxies in a completely different regime, orders of magnitude different. It can explain gravitational lensing through the deep void, and it can explain late time acceleration. It can explain the end of the exponential inflationary period after the Big Bang. One single framework, and when I plug it into neutron stars, again it fits like a hand in a glove. So that's the power of expanse tension theory. I believe I have a credible, theoretical explanation of glitchy, erratic neutron stars. Thank you for listening, and please subscribe, please watch further videos, go through the series. Expanse tension theory appears to have a power of explanation of anomalies, of the unexplained, of mysteries that we can't explain in the universe. Thank you very much for watching. Bye-bye.